Hello friends, this lecture is in continuation with the previous lecture where we learnt that the sum of all forms of energy of a system is called total energy, which consists of internal, kinetic and potential energy for simple compressible systems. Internal energy represents the molecular energy of a system and may exist in sensible, latent, chemical and nuclear forms. In today's lecture, we shall be discussing the concept of heat and the terminology associated with energy transfer by heat. Discuss the three mechanisms of heat transfer: conduction, convection and radiation. Temperature and heat. Energy can cross the boundary of a closed system in two distinct forms: heat and work. It is important to distinguish between these two forms of energy to form a sound basis for the development of the laws of thermodynamics. We know from experience that a can of cold soda left on a table eventually warms up and that a hot baked potato on the same table cools down. When a body is left in a medium that is at different temperature, energy transfer takes place between the body and the surrounding medium until thermal equilibrium is established. That is, the body and the medium reach the same temperature. The direction of energy transfer is always from the higher temperature body to the lower temperature one. Once the temperature equality is established, energy transfer stops. In the process described, energy is said to be transferred in the form of heat. Heat is defined as the form of energy that is transferred between two systems or a system and its surroundings by the virtue of a temperature difference. That is, an energy indication is heat only if it takes place because of a temperature difference. So, we note that there cannot be any heat transfer between two systems that are at the same temperature. Heat, unlike temperature, pressure and volume, is not intrinsic property of a system. Heat is energy in transition. It is recognized only as it crosses the boundary of a system. Consider the hot baked potato once more. The potato contains energy, but this energy is heat transfer only as it passes through the skin of the potato, that is, the system boundary, to reach the air. Once in the surroundings, the transferred heat becomes part of the internal energy of the surroundings. Thus, in thermodynamics, the term heat simply means heat transfer. Historical background on heat. Heat has always been perceived to be something that produces in us a sensation of warmth, and one would think that the nature of heat is one of the first things understood by mankind. However, it was only in the middle of the 19th century that we had a true physical understanding of the nature of heat. Heat was then defined as the energy associated with the random motion of atoms and molecules and was based on the caloric theory proposed by a French chemist. The caloric theory asserts that heat is a fluid like substance called the caloric, that is, a massless, colorless, odorless and tasteless substance that can be poured from one body into another. When caloric was added to a body, its temperature increased, and when caloric was removed from a body, its temperature decreased. When a body could not contain any more caloric, much the same way as when a glass of water could not dissolve any more salt or sugar, the body was said to be saturated with caloric. This interpretation gave rise to the terms saturated liquid and saturated vapor that are still in use today. The caloric theory came under attack soon after its introduction. It maintained that heat is a substance that could not be created or destroyed. Yet, it was known that heat can be generated indefinitely by rubbing one's hands together or rubbing two pieces of wood together. It was later the careful experiments of the Englishman James P. Joule that finally convinced the doubters that heat was not a substance after all, and thus put the caloric theory to rest. Although the caloric theory was totally abandoned in the middle of the 19th century, it contributed greatly to the development of thermodynamics and heat transfer. Heat and work. Here we look in some detail at how energy can be transferred as heat and work between a system and its environment. Let us take as our system a gas confined to a cylinder with a movable piston. The upward force on the piston due to the pressure of the confined gas is equal to the weight of the lead shot loaded onto the top of the piston. The walls of the cylinder are made of insulating material that does not allow any transfer of energy as heat. The bottom of the cylinder rests on a reservoir for thermal energy. A thermal reservoir whose temperature T you can control by turning a knob. The system, that is, the gas, starts from an initial state I, described by a pressure Pi, a volume Vi, and a temperature Ti. You want to change the system to a final state F, described by a pressure Pf, a volume Vf, and a temperature Tf. The procedure by which you change the system from its initial state to its final state is called a thermodynamic process. During such a process, energy may be transferred into the system from the thermal reservoir. Also, work can be done by the system to raise the loaded piston, that is positive work, or lower it, that is negative work. We assume that all such changes occur slowly, with the result that the system is always in thermal equilibrium, that is, every part of the system is always in thermal equilibrium with every other part. Suppose that you remove a few lead shot from the piston, allowing the gas to push the piston and remaining shot upward through a differential displacement ds with an upward force denoted by F. Since the displacement is tiny, we can assume that F is constant during the displacement. Then F has a magnitude that is equal to Pa, where P is the pressure of the gas and A is the face area of the piston. The differential work dW done by the gas during the displacement is given by F into ds, which comes out to be Pa into ds and is equal to P into A ds. And then dW is equal to P dV. Here dV is the differential change in the volume of the gas due to the movement of the piston. When you have removed enough shot to allow the gas to change its volume from Vi to Vf, the total work done by the gas is given by W is equal to integral dW and is equal to integral P dV from Vi to Vf. During the volume change, the pressure and temperature may also change. To evaluate this equation directly, we would need to know how pressure varies with volume for the actual process by which the system changes from state I to state F. State change procedure. There are actually many ways to take the gas from state I to state F. One way is shown in this part of the figure. This is a plot of the pressure of the gas versus its volume and is called a PV diagram. The curve here indicates that the pressure decreases as the volume increases. The integral in this equation, and thus the work done by the gas, is represented by the shaded area under the curve between points I to F. Regardless of what exactly we do to take the gas along the curve, the work is positive due to the fact that the gas increases its volume by forcing the piston upward. Another way to get from state I to state F is shown in part B of the figure. Here, the change takes place in two steps. The first from state I to a state A, and then the second from state A to state F. Step IA of this process is carried out at a constant pressure, which means that you leave undisturbed the lead shot that ride on top of the piston. You cause the volume to increase from Vi to Vf by slowly turning up the temperature control knob, raising the temperature of the gas to some higher value Ta. Increasing the temperature increases the force from the gas on the piston, moving it upward. During this step, positive work is done by the expanding gas and heat is absorbed by the system from the thermal reservoir. This heat is positive because it is added to the system. Step AF of the process is carried out at a constant volume, so you must wedge the piston, preventing it from moving. Then as you use the control knob to decrease the temperature, you find that the pressure drops from Pa to its final value Pf. During this step, heat is lost by the system to a thermal reservoir. For the overall process IAF, the work W, which is positive and is carried out only during step IA, is represented by the shaded area under the curve. Energy is transferred as heat during both steps IA and AF with a net energy transfer Q. Part C of the figure shows a process in which the previous two steps are carried out in reverse order. The work W in this case is smaller than from figure B, as is the net heat absorbed. Part D of figure suggests that you can make the work done by the gas as small as you want by following a path like ICDF, or as large as you want by following a path like IGHF. To sum up, a system can be taken from a given initial state to a given final state by an infinite number of processes. Heat may or may not be involved, and in general, the work W and the heat Q will have different values for different processes. So we say that heat and work are path dependent quantities. Part E of figure shows an example in which negative work is done by a system as some external force compresses the system, reducing its volume. The absolute value of the work done is still equal to the area beneath the curve, but because the gas is compressed, the work done by the gas is negative. Part F of the figure shows a thermodynamic cycle in which the system is taken from some initial state I to some other state F and then back to I. The net work done by the system during the cycle is the sum of the positive work done during the expansion and the negative work done during the compression. Here, the net work is positive because the area under the expansion curve, that is I to F, is greater than the area under the compression curve, that is from F to I. The first law of thermodynamics. You have just seen that when a system changes from a given initial state to a given final state, both the work and the heat depend on the nature of the process. Experimentally, however, we find a surprising thing. The quantity Q minus W is the same for all processes. It depends only on the initial and final states and does not depend at all on how the system gets from one to another. All other combinations of Q and W, including Q alone, W alone, Q plus W, and Q minus 2W, are path dependent. Only the quantity Q minus W is not. The quantity Q minus W must represent a change in some intrinsic property of the system. We call this property the internal energy E internal, and we write it as delta E internal is equal to E internal F minus E internal I and is equal to Q minus W. This equation is the first law of thermodynamics, that is, the internal energy of a system tends to increase if energy is added as heat and tends to decrease if energy is lost as work done by the system. As we discussed, the principle of energy conservation as it applies to isolated systems, that is, to a system in which no energy enters or leaves the system. The first law of thermodynamics is an extension of that principle to systems that are not isolated. In such cases, energy may be transferred into or out of the system as either work or heat. In our statement of the first law of thermodynamics, we assume that there are no changes in the kinetic energy or the potential energy of the system as a whole. The work done on a system is always the negative of the work done by the system. So, if we rewrite the first law of thermodynamic equation in terms of the work done on the system as delta E internal is equal to Q plus W on. This tells us that the internal energy of a system tends to increase if heat is absorbed by the system or if positive work is done on the system. Conversely, the internal energy tends to decrease if heat is lost by the system or if negative work is done on the system. Adiabatic process. A process during which there is no heat transfer is called an adiabatic process. The word adiabatic comes from the Greek word adiabatos, which means not to be passed. There are two ways a process can be adiabatic. Either the system is well insulated so that only a negligible amount of heat can pass through the boundary, or both the system and the surroundings are at the same temperature and therefore there is no driving force or temperature difference for heat transfer. An adiabatic process should not be confused with an isothermal process. Even though there is no heat transfer during an adiabatic process, the energy content and thus the temperature of a system can still be changed by other means such as work. As there is no heat transfer, we can put Q is equal to 0 in the first law equation and get delta E internal is equal to minus W. This tells us that if work is done by the system, that is, if W is positive, the internal energy of the system decreases by the amount of work. Conversely, if work is done on the system, that is, if W is negative, the internal energy of the system increases by that amount. This figure here shows an idealized adiabatic process. Heat cannot enter or leave the system because of the insulation. Thus, the only way energy can be transferred between the system and its environment is by work. If we remove shot from the piston and allow the gas to expand, the work done by the system, that is, the gas is positive and the internal energy of the gas decreases. If instead we add shot and compress the gas, the work done by the system is negative and the internal energy of the gas increases. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. Heat is energy that is transferred between a system and its environment because of a temperature difference between them. Heat absorbed by a material may change the material's physical state, for example, from solid to liquid or from liquid to gas. The principle of conservation of energy for a thermodynamic process is expressed in the first law of thermodynamics. So that is it for today. In the next lecture, we shall discuss energy transfer mechanisms. Thank you very much.